6 pi. Now, which orbital should come next? Pi star, yeah, because that is crummy overlap compared to the sigma. So those are going to be pi star. There we go. And then we finally get to 8 sigmas. Now we have to come up with symmetry labels for this. What's going to be the symmetry label for that sigma interaction?
G.
Yep, G. What about the anti-bonding?
U.
Yes. Okay. Now let's look at this pi interaction. It's U. And what's this one then?
G.
Shut. Reason is there's an inversion center here. The shaded in areas move up to the white regions move down to the shaded in regions. So they're going to flip. That's why I added that preface. Okay, now let's start tossing in electrons. How many more electrons do we need in our MOs? 6. So 1, 2, and remember these are degenerate, so you fill them at the same time. 3, 4, 5, 6. Okay, let's calculate the bond order. So we'll ask the question. What is the bond order? How many electrons do we have in bonding orbitals?
10.
Yep. 2, 4, 6, 8, 10. Anti-bonding?
4.
4. That's going to be a total of what?
3.
3.
You go to draw out. That bond, triple bond. Bingo bango, right? All right. Do you want to spend time drawing what the molecular orbitals look like after the atomic orbitals overlap, or do you feel comfortable, like you understand what's happening there?
So like the I think
Yeah, like when we did, like for the s orbitals, and then you resulted in something that looked a lot nicer than that, but it ended up that way. A lot of times it's easier to see the resulting interaction this way. When you guys actually go to look at some calculations later on this week, it's going to look more like this. The reason for that is it has to deal with the diffuse nature of orbitals, and that's just how it works. Okay, how are we doing on time?
3:35.
Okay, let's talk about one more set. Let's talk about heteronuclear diatomic molecules. So this is where they aren't the same. Why do I do that? Stay out there. So heteronuclear. Before we get there, we're going to return to the linear combination of atomic orbitals to make an MO. So the LCAOs, so returning to LCAOs for any diatomic. We got whatever our MO is. Do you remember what that linear combination looked like?
So like C1,
Yeah.
5, whatever, plus C2.
Yeah. So we're going to call this A, that one what are the A and B for? Yep, the atom. So atom A and atom B. And then these are whatever atomic orbital we're talking about. So in some cases, we've only seen it for hydrogen, where they only have one atomic orbital, but you may see a series of them lined up. Like for example, if you have nitrogen, you're going to have one S, a 2S, and then 3 2Ps included in here. Okay, so for a homonuclear diatomic, what's the relationship between Ca and Cb? For a homonuclear diatomic. Yep, they are the same. For a heteronuclear, that's where Ca does not equal Cb. So what we're going to do next, and that's generally, should put generally, meaning most of the time. There's always probably going to be a case for that isn't true. Now let's look at a situation where we're comparing two atomic orbitals that are different to one another. And let's see what happens to the corresponding molecular orbitals. So, we're going to consider electronegativities. Okay, so we're going to have 3 situations. One where the electronegativity of A is equal to the electronegativity of B. One where the electronegativity of A is greater than that of electronegativity of B. And then you can guess what the last one's going to be. En of A less than. We've seen this molecular orbital a couple times already. We have A over here, we have B over here, and we're looking at that. What do we know about the atomic orbitals?
They're at the same energy level.
Yep, they're at the same energy level. What we're going to get is something like that. Okay. What about if the electronegativity of A is greater than that of B?
A is going to be lower.
A, yep.
Closer to the bonding equilibrium.
Yes. Why?
Because if the electrons hopped up through it, it'd be lower in energy. That's a guess how.
Yeah, okay. That's not quite what happened. Well, that's not a bad way to think about it. So that's a good way, because you know that, all right, that one has to predominantly have more control over the electron density, right? So what do you know about the orbital contributions? So,
Greater.
yep, that one's got to be greater, at least in the bonding combination. It's got to be greater. Okay, so A is going to be lower than B. So A will be down here. We're going to put B up at that point, and then we have A, B. They're going to overlap. And that's what you're going to get. What about for the opposite? Same thing, just opposite. Yeah, the same thing, just opposite. It actually was not a smart ass question. It was. That's okay. So yeah, it's going to be the opposite in that case. And what we're going to see, not in this chapter, but next chapter. No, that's next chapter is this can be used to explain Lewis acids and bases and a ton of different properties of water. Like how does water behave as an oxidizing, as a reducing agent? Why is it that the hydrogens, like yeah, there is the whole argument that the H's are slightly positive and slightly negative, but that isn't the complete story on why, if you look at a water molecule, and let's say you have an anion, why do the H's? There's a ton of stuff you can explain with this. And then when you get into even more weird, complicated bonding, this is kind of how you have to think of it. So that's where we're going to lead. Next time we're done for the day. So we'll talk about also the resulting coefficients of the bonding and anti-bonding MO next time. Are there any questions about what we talked about today? Try your best to read this chapter. It's pretty dense, but it is helpful. And kind of everything else depends on this chapter for the rest of this semester. Yes. But we're going to go into more practical stuff rather than theoretical mumbo jumbo. All right. So no questions?